Okay, today, electromagnetic moment, but it'll take us a while. We won't be able to do it immediately. So after all this immense amount of formalism, we finally do something. We apply to it, and that brings us to 1948. And as I explained last time, there has been not a new idea in quantum field theory since 48. This will make lots of my colleagues very unhappy. And as the mic is now on me, you can, talk to each other to your heart's content without Ed Greco complaining about your behavior. He's used to better than me, I can tell. So the setup is, and the experiment is totally amazing. Has a Nobel Prize for it. Experiment is a ball like this. It's a kind of experiments that we have in low temperature physics here. So there's a ball, there's a magnetic field, not very strong. You put an electron and it goes there for a month or two, just stays there spinning around. And while it does that, it slowly processes because it has its internal spin. And there is an extra procession called anomalous procession, the one not predicted by Dirac. So what we'll do first, we'll get the Dirac result. And Dirac result was the first vindication on Dirac equation. I mean, he did it almost immediately after he derived the equation. So this is not quantum field theory. This is just relativistic quantum mechanics, Dirac version. So we have external magnetic field. So the Dirac equation in this magnetic field is this, where d mu is the covariant derivative electromagnetic couple and the vector potential. Now we'll derive this two ways. So one is we will act on this with, we'll multiply by covariant potential plus covariant derivative plus m. Which is a minus d square covariant derivative square minus m. Equals here. And then we can work out this covariant, this product here is G mu, derivative mu. And we can symmetrize and anti-symmetrize this product. So we can write this as 1/2 anti-commutator of G mu plus 1/2 commutator G mu. Now the anti-commutator gives us just G mu nu, the Minkowski metric. So we get from the first time, we just get a Laplacian, Minkowski Laplacian with time-like component minus the space-like component. And this term, we gave it a name. Let's see. So before we introduced antisymmetric tensor with two indices formed by the anti-commutator. So this becomes a minus I over I sigma mu mu. Except this is something one absolutely must not do in this part of the course, because the whole point of the course will be to get a factor 1/2. So now I'm a little bit flustered because I don't know how I did it, but I'm following the right now. So apparently the z doesn't have this 1/2. So we get 1 over 2, and you correct me if I'm wrong with something. Ah, no, it's okay. Ah, good. We write this now, but okay. How do you let me get away with this? What's going on? You're not even talking to each other.
The second term should be 0.
No, but these are covariant derivatives. What am I doing? Yeah, it's covariant derivative, right? So this is the covariant derivative squared. This is not the Laplacian, covariant derivative squared. And here we can write this part, because it's antisymmetric. We can write this as d mu commutator 1/2. So this thing absorbs 1/2, but there's another 1/2 that comes as a commutator. And you remember this is all 4x4 matrices. So this is multiplying the unit matrix in a 4x4 spinorial space. And then we have to compute what this commutator is. And when we substitute d mu minus I E mu here, then if you have two derivatives, that's symmetric, so they'll drop out. And if you have two a's, they'll also be symmetric, so they'll drop out. The thing that doesn't commute is a combination of the derivative. So we'll survive from this part. Commutator. There'll be only the cross term. And then, you know, some people like this fancy notation, but it just means minus IE d mu a nu minus d mu a nu. Is that okay? I have a thumbs up from the audience, which is good.
These that 1/2 and from the sigma.
Yeah, that was the whole trick. So what we did is we replaced this by 1/2 commutator. So 1/1/2 went away, but this one stayed. Because it's 1/2 that has to do with the commutator. And we are using the fact that this is antisymmetric, so only antisymmetric combination here works. And it has to be 1/2 because, you know, if I write it twice, it's 2 terms. You know, this is the same as 1/2 d mu d nu minus d nu d mu. And if I multiply something antisymmetric, they contribute both with the same value because, you know, I'm just changing the dummy labels when I'm summing it up. Okay? Everybody's okay? Somebody's okay with this? All right. I mean, you know, Ed Greco, God, I almost went off the boat. Ed Greco might be dissatisfied with you, but I'm very happy with this class. I can't tell you how happy I am. Just, you're really great. Okay. So, so only this survives from this commutator. So the Dirac equation now takes form covariant derivative squared minus e over 2. See, the I got absorbed into definition of sigma. E over 2 sigma mu nu. And we recognize this object as minus I, equals minus I E F mu nu, right? That's the definition of the of electromagnetic tensor. If this was Young-Mills theory, there'll be some extra stuff. But for abelian theory, that's all there is to it. Acting on the spinorial wave function is 0. So this is just true in general whenever you have electromagnetic field. The spinorial part satisfies this equation. And you know, this, as you'll see, this is explicitly pulling out a spin 1/2 term. This matrix is there. So what's wrong with this equation? It's really wrong. What is it missing? Yes, there is no mass in this equation. That's bad news. Okay. And the sign is, you know, there was a minus sign here and minus sign here acting on psi equals 0. So I multiply both sides by minus sign. So
M squared.
M square, even worse. Thank you. You're like rebooting. I mean, you're slowly coming up. So in a few minutes, it'll all be clicking. Okay. So that's just generally true, and you know, you might object, why did I multiply this? But as you'll see, this will be related we'll understand this term for boson theory, because remember, we do this kind of things when we want to write the Dirac equation to Klein-Gordon equation. We square this thing. I'll get to that in a second. But let me first describe the physical setup, which is what happens when this vector potential is not a quantum thing, but it's just a classical but very weak potential corresponding to a weak magnetic field. So classically, we have in our rest frame in the lab, we have a magnetic field, and we'll choose it to point upwards. So you'll have only a Z component. And then by the definition of Maxwell's electromagnetic tensor, for magnetic field, there's a Levi-Civita tensor saying 1, 2 is related to the third component. So it's related to that. And that, by definition of the tensor, is A1 minus, where these are vectorial spatial indices, A2. That's just the definition of that tensor. And we can choose A0 to be 0 and A1 and A2 vector potential components to be cooked up in such a way that one depends on the Y component, this one, times B, and the other one depends on the X component, and B is just constant. It's just strength of classical field. X times B. And if you substitute that in, you see that this is correct. It gives you the desired magnetic field. So, in some sense we're using gauge invariance, but anyway, just very simple construction. And we'll assume B small, so we'll drop B square terms in what follows. So now we can evaluate the covariant derivative the spatial component of it is minus the square. And here what will happen is the time component will have no contribution because A0 is 0, so that won't show up. So the only important will be three-dimensional Laplacian minus IE then I'm just squaring this thing here, so that's okay. Then we pick up from covariant derivative, we pick the cross, pick up the cross term, so that's why minus IE is there. That's this one, minus IE. And then we have this term minus the other term. These are spatial indices. And there would be another term, but it's of order B square, so we'll drop it. And now we have to remember just one little thing. This is actually acting, these derivatives are acting on the spinorial wave function. So what I can do is I can write this term as derivative acting on A, the vector potential. Sorry, there was a plus here. Was there a plus here? Yeah, the cross terms came with the same sign. So I can write this term as this plus A just acting whatever is on the right of this function. Now, you know, this is a divergence, and you know that divergences have to do with charges, etc. So you can check that this equals 0 by this definition. You know, because derivative with respect to x gives you 0, and derivative with respect to y gives you 0, and derivative with respect to 0. So this first divergence term is 0. The second term shows up twice. So we get delta square minus IE times 2 times this term. The 2 came from this showing up twice. So covariant derivative square has this 3 Laplacian here. And now I can expand this in terms of you know, A times dot in terms of my explicit formula with respect to B. And I get a factor of 2, factor 1/2 from here, right? Okay, let me just write it and get the factors right. IE B you know, there's an overall factor of B for a constant magnetic field for all terms, and there is x times dy minus y times dx plus order B square. And you know, this was just obtained. This is a dot product. So the first term, non-zero term, is A1. So it gives me this y with a minus sign.
Why is there a plus sign in the commutator? Not the del dot A plus A dot del?
Right here?
Yeah. Why?
This is not a plus sign. You know, we squared this thing, covariant derivative. Then we got a square of that. That's the first term. And then we got 2 terms which are cross terms. These are 2 terms which are cross terms, so they appear with the same sign. It's just a square of this quantity, so there is no commutator. And then we drop the AA term, which should be there, but it's dropped in the weak magnetic field limit.
Where do you get the second A dot del term?
This one?
The second one. So
this one. Oh, the second one? How I got 2 here?
Yes.
Yeah, when I look at this, you know, what this term is doing, it's a derivative times A acting on a function psi, on a spinorial function.
Okay.
So this derivative acts on everybody to the right of it. So it has two terms. And I'm putting this off camera, but it doesn't matter. It has a term which is its derivative of this field by itself times psi plus Leibniz rule, its dot derivative of the wave function. So that's where it came from. The second, this T2 is important, right? Because it's all about factors of 2. So now, yes, I'm still just computing a square. Now I can rewrite this square in a way you're used to from ordinary electrodynamics. You know, this is something in direction x multiplied by something in direction y, so this is a cross product. And B is acting in direction z. So I can write this as minus EB dot, this first term psi cross, you know, usual cross product, times P. That's the first term. Well, and the second term, and you know, now this is a 3 vector having components z, x, y, and z. Because this is pointing in direction z, this will only be x's and y's. And the first term is this one, and the second term is that one. And the 2's have cancelled out, so there is minus I EB. So result of this is that we have shown that we have, well, this you recognize as the angular momentum. X cross P is the angular momentum. So this is called orbital momentum in quantum mechanics. You know, you're that far away and you're moving as momentum P. So this is orbital angular momentum.
Does the momentum have the I?
It does, and that's important, thanks. I went into it. And there's an H bar which we set to 1, but you're absolutely right. And I hope that I got the sign right. An important sign, I hope I got it right. But, oh, you know, so what you're seeing here is you're getting from covariant derivative, you're getting the combination B dot the angular momentum times the strength of magnetic field. So for example, if you had a Klein-Gordon charge field, so a Klein-Gordon charge field. We would find that d mu times d mu. For that case, we are looking only in that term. There are no gamma matrices for. We would find that d mu plus m square acting on the charged field psi can be interpreted in a rest frame and weak field. This can be interpreted as just the Laplacian minus EB dot angular momentum plus term that's higher in B. which we cross out, times psi. So for the scalar field, we only get angular momentum, orbital momentum. But for Dirac case, we get an extra term. Now, to understand this extra term, we will now have to go to Dirac equation in a rest frame. Now, to give it the usual non-relativistic interpretation in quantum mechanics. So I think I can erase everything up to here. And spin magnetic moment. You know, we can use the Dirac basis we started with, the original, which is convenient to. So there are you know, two things about group theory. One is, if you're doing a covariant calculations, then these explicit representations are just a nuisance. They're useless. But if you're doing a calculation in specific frame, so you know our Euclidean 3 dimensions are embedded in the Minkowski world. So we're looking at a subgroup. Then looking at specific representation is useful because they tell you how the SO3 world is embedded in SO4 world if you're in the rest frame. So that's the time where my injunction against having explicit representation doesn't apply. So in Dirac basis, the sigma, this guy, the spatial part of it, is written as Levi-Civita tensor in these two indices, K, sigma K, 0, 0. So, you know, this runs over 3 values and they have to be different. So this just pulls out the third. If this is 1, 2, then this is sigma 3, etc. There are no sums involved in this because Levi-Civita tensor is either 1, -1, or 0. And it's 1 if it's increasing sequence of integer, it's -1 for any transposition, it's 0 if anything repeats. So there are no sums involved in this. And this is not Pauli. That's because we're trying to relate it to the ordinary rest frame mechanics. So then e to the 2, this guy here, in the rest frame, becomes e square sigma 3 F12 minus F21. The reason why this happens is the way we have constructed our field is that the magnetic field was in the z directions, so these are the only non-zero components in 3 dimensions. X and Y components when magnetic field is normal to that time. So only sigma 3 gets picked up. That's from this. And you know, and they show up with opposite signs. And again, you're supposed to keep sign of all signs and especially factors of 2. So this is then very simple, because this is just B, the strength of a magnetic field. So this is E over 2, and it happens twice because this is antisymmetric. So this was defined to be B, and this was defined to be minus B, the strength in Z direction. So it's 2 sigma 3 B, which is then conventionally called 2E. This object here is called spin in quantum mechanics. This becomes magnetic field times the spin.
Why is it 2E?
Just a second. Yeah, I mean, okay. Let me just be more explicit. In quantum mechanics, the spin operator is Pauli matrix divided by 2. Okay. So it comes, this 2 cancel, and that one comes from definition of spin operator in ordinary quantum mechanics. So the result of all this